Today we're going to be talking about the area of regular polygons. Before we do that though, let's take a minute to review the formulas for the figures that we've already learned. Before I go through these, take a minute to pause the video and write down the ones that you can remember and then check that as we go through this. Okay, so the formula for the area of a rectangle is base times height. If you still think of it as length times width, that's okay, but remember the terminology that we're going to be seeing is base times height. For a parallelogram, we have the area as base times height. For a triangle, area is 1/2 times the base times the height. For a trapezoid, we have 1/2 times the height times the sum of the two bases. For a rhombus, we use the diagonals, so the height is 1/2 times the product of the two diagonals. And for a kite, it's the same as a rhombus, so we have 1/2 times the product of the two diagonals. Now, as we get started talking about the area of a regular polygon, we do need to talk about a few terms that are going to come up as we learn this. They are the center of the polygon, the radius of a polygon, and an apothem. Now, the definition for the center of a polygon is the center of the circle circumscribed about the polygon. And you'll remember that circumscribed about means that it goes around the outside, and each of the vertices of our polygon are on the circle. Now, the radius of the polygon has a definition of the distance from the center to a vertex. So the radius of the polygon is the same as the radius of the circle that is circumscribed about the polygon. The apothem, on the other hand, is still a distance, but it's the perpendicular distance from the center to a side of the polygon. So it goes from the center to a side, and it's perpendicular. And this does two things. One, it bisects the side that it intersects, and two, it bisects the angle. Because as you'll recall, all of the radii are going to be the same because it's a radius of a circle, so they're congruent, which means that this is an isosceles triangle, and the perpendicular distance or the altitude of an isosceles triangle bisects the vertex angle and the opposite side. And that's going to be important as we go through this lesson. To start off with, we can use that information to find the measures of angles in a polygon. If we start with finding the measure of angle 1, it's this vertex angle. And you'll notice it's one of actually 5 in this pentagon. So if I think about the fact that I have 5 angle 1s, then the measure of angle 1 is really the whole thing, which is 360 degrees, divided by 5, and so we get a measure of 72. Now, as I mentioned before, angle 2, which is right in here, is the bisected angle of angle 1. So the measure of angle 2 is actually 1/2 of the measure of angle 1. And since the measure of angle 1 is 72, we take half of that and we get 36. And then finally, the measure of angle 3, it's the third angle in this triangle. Well, we know that all 3 angles in a triangle add up to 180. So if I take that total of 180 and subtract from it the measure of angle 2, which is 36, and also subtract the measure of this other angle, which is a right angle, then I get a measurement of 54. If we look at another example, now we have an octagon instead of a pentagon. The measure of angle 1 is still an angle at the center. So we're going to do the same thing. We're going to take the total angle measure, which would be 360 if you go all the way around the center. Divide it by 8, since there are 8 of those as you go around, even though we only have half of this one showing. So we get 360 divided by 8, and we have a measure of 45 degrees. The measure of angle 2, since it's here, it's half of this angle, which is the same as angle 1, so we're going to do 1/2 of 45, and we get 22.5. For the measure of angle 3, it's in this triangle with angle 2 and also a right angle, so we can do 180 minus the 90 degrees for the right angle minus the 22.5 degrees for angle 2, and we get a measure of 67.5. Now, as we're going to be finding the area of these polygons, the concept of having triangles is going to remain important. So let's talk first about triangles. We know that the area of a triangle is 1/2 times the base times the height. And in this figure, we have 5 of those triangles. So the area of my pentagon is going to be 5 times the area of this particular triangle. Okay? Now, if we think about the base of this triangle, that's this distance right here. It's actually the side of the pentagon. Could be the side of whatever polygon we're working with. In this case, it's the pentagon. The height of this pentagon, or of this triangle rather, is the apothem. So if I think of the area of this triangle rather than being base times height, it's actually 1/2 times the side of the polygon times the apothem. Well, since it's a pentagon and I have 5 of those, I have 5 times 1/2 times the side times the apothem. And if I rewrite this a little bit, I'm going to have 1/2 times 5 times the side length times the apothem. 5 times the side length is 5 times this side length, so we have 1, 2, 3, 4, 5. It's actually the same as the perimeter. So we can rewrite this formula as 1/2 times the perimeter of my polygon times the apothem of my polygon. And this is the formula that we're going to use as we find the area. So if we start with this first example, we want to find the area of the regular decagon over here. We know that the side length is 8 and the apothem is 12.3 inches. So we have our formula of area equals 1/2 times the perimeter times the apothem. So we have 1/2. Now the perimeter is going to be the side length times the number of sides. So I have 8 times 10 times my apothem of 12.3. And when I put that into my calculator or figure it by hand, whichever you'd like to do, we get 492. Our unit is inches, so our answer for area is in inches squared. Now this next example, we're now finding a regular pentagon, so we're going to have 5 sides. So again, we start with our formula, 1/2 times the perimeter times the apothem. So we have 1/2. Now for my perimeter, I'm going to have 5 times the side length. It tells me the side length is 11.6 centimeters, so I have 5 times 11.6 times my apothem of 8 centimeters. If I multiply that out, I get 232. My unit is centimeters squared. Sometimes it gets a little more complicated because we're not given complete information, or it seems like we're not given complete information, but we can find it based on what we do have. So in this example, a honeycomb is made up of regular hexagonal cells. So we're going to draw a hexagon. That's a bad hexagon, but we'll work with it. The length of one side is 3 millimeters. What is the area of the cell? Well, if I draw in one of the triangles, right, and here's my apothem, I'm going to draw that a little bit bigger out here over the side, and that's what we're going to focus on. Okay, so here's my apothem. Now, since the side length is 3 millimeters, that's the base of this triangle. Since this is bisected, I know that this part right here is 1.5. It's half of that. Now, since this is a hexagon, I know that each central angle, this whole angle, is going to be 360 divided by 6, which is 60. Well, since this is bisected, that means this is 30, which means that this angle here is 60 degrees. And now I have a 30, 60, 90 right triangle. So this will help me find the length of my apothem. If you recall from a 30, 60, 90 right triangle, the angle opposite, or the side opposite your 30-degree angle, if you consider it to be S, the side opposite your 60-degree angle is that S times the square root of 3. So my apothem is actually 1.5 times the square root of 3. So now we have enough information to use our formula to find the area of this polygon. So we have 1/2 times the apothem, which is 1.5 times the square root of 3, times the perimeter, which is going to be 6 sides times 3 millimeters on each side. When we put that into our calculator, we want to multiply all of the numbers outside the radical, so 1/2 times 1.5 times 6 times 3, we get 13.5, and then we have the number under the radical. This is the exact answer. If I want to find an approximate answer, then I would do in my calculator 13.5 times the square root of 3, and I would get 23.38 if I round it to the nearest hundredth. My unit is millimeters squared. Now for number 6, we have the side of a regular hexagon, so we're going to have the same kind of figure. And this side is 16 feet. Now I'm just going to start by drawing the triangle, and we know we're going to have 6 of these because we have a hexagon. Now my side length is 16 feet, so this whole thing is 16 feet, which means this part right here is 8 feet. Now just as before, I know this angle is 30, this angle is 60, so my apothem is going to be the side length times the square root of 3, or 8 times the square root of 3. So when I have my formula, 1/2 times the perimeter times the apothem, we plug in our numbers, 1/2. Now the perimeter is going to be my 6 sides times my side length of 16. My apothem is 8 times the square root of 3. We do the multiplication, and this wants it to the nearest square foot, so we're not going to look for an exact answer. We just want to put it into the calculator and find our approximate answer. Now when we get the approximate answer, we find that it is 665.11 if I take it out 2 decimal places. Well, to the nearest square foot, that is 665 square feet. So that's it for finding the area of regular polygons. Let's review all the different formulas that we've covered so far. The area of a parallelogram, which is also a rectangle, that's why I don't have it listed twice, is base times height. The triangle, as you will recall, the area is 1/2 times the base times the height. The area of the trapezoid is 1/2 times the height times the sum of the 2 bases. For a rhombus, we use the diagonals, and it is 1/2 times the product of the 2 diagonals. A kite is going to have the same formula as a rhombus, so it's 1/2 times the product of the 2 diagonals. And the regular polygon, the formula that we just learned, is 1/2 times the perimeter times the apothem. And remember, the perimeter is going to be the number of sides in times the side length of S. So you could also look at this formula as 1/2 times N times S times A, where this is the same as P.